Hi everyone. In this video we're going to be working through the material, or talking about the material anyways, in section 1.2 of your textbook. And that material includes talking about the difference between designed experiments and observational studies, and also the difference between a confounding variable and a lurking variable. So some new vocabulary. In an observational study, it kind of is what it sounds like. You simply observe a sample group and you take measurements, right? So the measurements is what gives you your data. And you're not actually doing anything actively to affect the result. So a good example of this type of observational study would be like a political opinion poll, right? And so every election cycle, the University of Texas at Austin polls Austin residents about which presidential candidate they prefer. And so they don't do anything to affect the result. They're not trying to coach people on what to answer, right? And all they're really doing is taking a measurement of their sample, right? So the sample here would be, the people they reach either online or in an email or on a phone call or what have you. And the measurement is just getting what presidential candidate they prefer. On the other hand, in a designed experiment, you do actively do things to influence the result, right? So we are actually actively influencing the result of the measurements in a designed experiment, right? This is the difference between an observational study and an experiment. And so generally, in a good experiment with a decent design, you want to split the individual in your sample into two different groups. And so one of them we call the experimental group, and one of them we call the control group. And what we do is we apply some treatment to the experimental group, and you measure some value of interest and compare it with a control group, right? And so one example that I can think of here is maybe you are testing different fertilizers, right? And so you have, some kind of plant that you're growing over here, and you have let's say you have a whole farm worth of plants, right? And to save time, I'm just going to draw like 8 little circles for 8 little plants. And what we're going to do is divide up the farm so that half of it lies in an experimental group, and the other half lies in my control group. And what we're going to do is we're actually going to take fertilizer and apply it to all of the plants in my experimental group, but the control group does not receive the treatment. And hopefully every other kind of variable that might affect the outcome of the growth of these plants holds the same. Since they're on the same farm, hopefully they receive the same amount of sunlight and the same amount of rain and are otherwise treated exactly the same, except that the control group will not receive the fertilizer. Now at the end of some set period of time, like the end of a growing season, you compare the yields, and if you compare the yields of the experimental group to the control group and you find that there's no change, then maybe that fertilizer wasn't so great. If you find that the experimental group did better than the control group, then you actually have a good fertilizer candidate. Excuse me, having some kind of technical issue here. Okay, here we go. And heck, here's another example for you as a designed experiment, right? So this says a researcher wants to know whether some chemical, some nicotinamide riboside, is effective in increasing the lifespan of mice. And so maybe you have 50 mice, and you assign them to an experimental group, and you give 50 mice a placebo every day. So let me repeat that. The 50 mice in the experimental group are actually given the drug, the nicotinamide riboside, every day. And then in the control group, you have another 50 mice that don't receive a drug. Maybe they receive a capsule with the same filler that's used as in the capsule of nicotinamide riboside, but they're not actually given the drug you're trying to study. And after all the mice die, maybe you compare the lifespan between the two groups, and if the nicotinamide riboside is effective, then what you should see is you should see that the experimental group has a larger, or a greater average lifespan than in the control group, or in the placebo group. All right, so this slide might be a little bit confusing at first because I know there's a lot to look at. But back in the day, in this journal, the American Statistician, in 1996 it looks like, they posted this table, and I want to explain this table to you because what it shows is a little bit counterintuitive. What this is showing is the result of a study in which they tracked a number of smokers. So they actually looked after like 1,314 people. Sorry, I guess they weren't all smokers. I guess 582 of these people were smokers, and then 732 were non-smokers. And they watched these people, this 1,314 people, for I think a period of something like 10 years or maybe 15 years. I can't remember how long, but it was a pretty significant time period. And they counted at the end of the time period how many were dead from each group. So among the smokers, after 10 or 15 years or so, 139 of them had died. And out of the non-smokers, out of 732 non-smokers, they found that 230 had died. And if you do this fraction for each group, if you calculate number of dead divided by the number of total that you began with in the group, this is what calculates the odds of death, right? So 139 out of 582 means that about 31% of the smokers died during that 10 or 15 year time period. Then 230 out of 732 gives you that about 46% of the non-smokers died during the same time period. And this is a little bit counterintuitive because we all know that smoking is not good for you. Smoking is generally bad for your health. It causes all sorts of respiratory problems, not to mention lung cancer. So I would have expected, and I think we can all agree that we would have expected smoking status, yes, to mean an increase in odds of death versus the non-smokers. And this is not what they found in the observational study here. The last thing I want to explain before I move to the next slide is where it says OR. That means odds ratio. And so the way we calculated this OR is actually that 31% divided by 46%. And that's how we get 0.658. And so to explain, an OR of less than 1 would mean that smokers are living longer than the non-smokers. Or smokers have a lower risk of mortality than the non-smokers, right? And an OR of greater than 1 would be actually what we expect. If we had an OR greater than 1, that would tell us that non-smokers had a lower risk of mortality than smokers. So we expected an OR greater than 1, and in the end, with the study, we calculated an OR less than 1. Now let me explain why that happened. On this slide here, we divide up the same data, right? So we're looking at the same people that were tracked by the study, but this time we're going to divide them up by age group. So we have an age group of 18 to 34-year-olds, an age group of 35 to 54-year-olds, an age group of 55 to 65-year-olds, and then people who are older than 65. And when I divide them up into age group, and we do the same analysis, we count how many were dead at the end of the interval, and we calculate their, percent mortality of each group, and we calculate the same odds ratio, we find that for each of these 4 age groups, the odd ratio is greater than 1. some of these groups are pretty close to 1, because if they're really young, you don't expect, necessarily smoking to mean you have an increased chance of death, at least not by that much. And if you're really old, maybe that doesn't mean quite as much. But what we found is, at least for these middle-age groups, between 35 and 65, smoking made a significant difference in terms of, this odd ratio being greater than 1. That tells us that these smokers did have a significantly increased chance of mortality. But that's kind of interesting, isn't it? Because over here, it looks like smokers have a lower risk of mortality. And over here, with the same data, we can show that smokers have a greater risk of mortality. And I want to draw your attention to the reason here. What I'm trying to get at is that in this study, it really looks like they picked really old non-smokers. So among the people who do not smoke, the number that were 65 and up is really, really large. Like 165 plus 28, that's like 193, I think, non-smokers. And in the same group, the oldest age group, they actually only had 49 that belonged to the smoking status, right? So they were able to conclude that, smoking evidently, according to this odds ratio, does not increase your risk of mortality, basically by stacking the study. They were only choosing non-smokers who were really old and were likely to die anyways just because of their age. And so you have to be a little bit careful when you're reading results of studies, right? You have to look out for what we're calling, in this case, lurking variables. And we haven't introduced this yet, and so you haven't seen it yet, but it's spelled Lurking. And lurking variables are things that, usually the researcher is unaware of the presence of lurking variables, but the lurking variables can explain the results of your study, your survey or your experiment, and kind of ruin your conclusion here, right? And so we got this really weird result from this study because of our lurking variable. In this case, our lurking variable was the age of the participants in each group. So really, it was the age of the participants. What we found here, this odds ratio, does not say much about smoking. What this odds ratio tells us is that older people have a higher risk of mortality than younger people, right? Anyways, this is a kind of a silly example of lurking variables. Now, kind of getting to the point, a lurking variable is a factor influencing the result of an experiment or study, which is not considered by the study. The presence of a lurking variable, of course, invalidates the results, just like these results over here were just completely ridiculous because of the presence of a lurking variable. Another example to this point. I read a few years ago of a study that claimed that drinking coffee correlated with longevity, meaning that people who drink coffee live longer than people who don't drink coffee. And kind of the interesting point here is that people who drink coffee tend to have office jobs where they have, a coffee pot in the break room, and it's really tempting to grab a cup of coffee on the way to your office. And if you have an office job, chances are that you make more money and that you are exposed to less risk at work, right? So in an office job, there's not many things that can make you die early. But if you work, a lot of manual labor, sometimes those are dangerous or hazardous jobs, right? And so if you have more money, maybe you have a better diet, maybe you have access to better, gyms or exercise equipment or better health care. And you also have a less dangerous job. And if you do not drink coffee, maybe that means you live in a poorer country, or maybe you just don't have an office job, right? Maybe you work in a job where you, you're working out in the field, it's more dangerous, so you're more likely to die young. And maybe those jobs pay less. And this is just, generalizing. This is obviously not the rule everywhere, right? You can find jobs in the field that pay more than office jobs. But just as a general rule, these things sort of hold. And my purpose of bringing this up is just to say that when this study was originally claiming that coffee could extend your lifespan, the conclusion doesn't always follow from the correlation, is what I'm trying to say. Sometimes just because the people who are living longer also drink more coffee doesn't necessarily mean that coffee is good for you or that coffee drinking is healthy. So a confounding variable is a variable that is difficult or impossible to separate from the variable we desire to study, but might also have the same effect. And I'll admit to you that confounding variables and lurking variables sound very similar in their definition, but I think it's important for your homework and your exam that you understand the difference. And so, as an example of a confounding variable, let's talk about this. A study is seeking to find whether regular broccoli consumption extends human lifespan. So if you eat broccoli every day, does that make you live longer? What would be some possible confounding variables here? I can think of one or maybe two really big possible confounding variables. Number one would be the other items that are frequently in the diet of the individuals that belong to this experiment. And then maybe other lifestyle choices as well. Like, for example, exercise. And I'd say that these are confounding variables because if you're performing some kind of study, you have a group of people that you're observing that is, let's say, the experimental group. So the experimental group in this case would be the group of broccoli eaters, or our broccoli group. And then you would also need a group of people that are not eating broccoli, so our control group. And you would want to compare lifespan between your broccoli group and your control group who is not eating broccoli. Now, the confounding variables here are other items in the diet, because if you have a group of people that likes to eat broccoli or is motivated to eat broccoli, I bet the rest of the things in their diet are also healthy, right? They're more likely to eat maybe fish and grilled chicken versus, fried chicken or steak. And maybe if you're committed enough to your health to eat broccoli on a regular basis, maybe you also exercise on a regular basis. Whereas if you, if you're not someone who eats vegetables on a regular basis, maybe you also don't care too much about your health, and so you're not really into exercise either. And so these things would also extend lifespan just based on the conventional wisdom. And they would also tend to be characteristics of the broccoli group more so than the broccoli haters. And so this is what makes it a confounding variable, where a confounding variable is a variable that is difficult or impossible to separate from the variable we desire to study. So what we want to study here, the variable we want to study, is the effect of broccoli on lifespan. But what's difficult to separate is the effect of exercise on lifespan and the effect of other diet factors on lifespan, because those might also have the same effect of increasing lifespan. So it would be difficult to study just broccoli, just the effect of broccoli, Again, and it's important to know the difference between lurking and confounding variables, and so I just put together this quick little summary. For a lurking variable, generally the researchers involved in the study are unaware of the presence of the lurking variable. Whereas with a confounding variable, usually the researchers are aware that there's a confounding variable present. A lurking variable does affect the response that we're trying to observe, and a confounding variable is one that we expect to create the same response as the one we're trying to observe, right? And a lurking variable, of course, invalidates the data, and a confounding variable can definitely invalidate data, if you don't somehow find an adequate way to separate the confounding variable from the variable we're trying to study. As one final note before I end the video, observational studies can be performed retrospectively, and retrospectively just means you look back through historical records for correlations. And I actually had a buddy of mine in college who did this. He was looking back through historical records of a hospital, and I can't remember exactly what he was looking for correlations between, but it was between a few like medical diagnoses, right? And so he didn't have to plan his study and then collect data as it happens in the future, like we normally do with a study, but he actually planned his study and then actually looked back through the records that were already taken to collect his data.